Okay, let's do one that is second order. So let's take some data. Okay, so the way we've been doing this is we are going to plug this into our calculator. And let's remember that we want to graph this data and find out which of these provides a straight line. We've got three options. We know that zero order will be a straight line if it's just time versus the straight concentration of A. And we know that first order will be a straight line when it's time versus the natural log of A. Let's get rid of those zeros. We don't need those. That means at the beginning, and we're not talking about the beginning. Here is a second order reaction where time versus the inverse of A gives us the straightest line. So let's get our calculator ready for this. And we want to clear all the data. So there's lots of ways that we can do this. One of them is to go to statistics and hit clear list. And I have varying luck with this one. So another way I'm going to do it is I'm going to hit second and the plus sign, and notice that this says memory. So when I do this, it brings up the option for clear all lists. So we'll do that one, clear all lists. And this should clear out all of the data in our statistics. So let's make sure that we're clear. Okay, good. So what we're going to do is we're going to take these data, I'll zoom in a little bit, and we're going to plug these into our calculator and run a couple of tests to see which order this is. So let's bust out our calculator. Now what we want is to put time in L1. All right, so notice that here in L1 we've got 0, 1000, and I'm entering these data just straight down as they appear. And I'm doing this as meticulously as I can, because we want to make sure that we don't have any errors in our data that throws everything off. So I'm going down this line, 5200, and I'm entering my time in L1. It doesn't really matter what column you put it in as long as you know where it is when you plot it. Okay, so there is L1. That's our time. We're going to do the same thing for L2. And this is going to be our concentration. So our initial concentration at time 0 is 0.01. There's no need to enter all of these zeros. In fact, watch what happens when I try. If I enter 0.01000, the calculator is just going to say 0.01. So it's going to smooth it out for you. 0.00625. This is 0.00476. I know this calculator is a lot slower than yours. I'm doing it with my mouse and it takes a while. 0.00370. 0.00313. 0.0027. There's really no need to enter the final zero. You'll see what I'm talking about. The calculator cuts it out. 0.00241. And finally 0.00208. Okay. So what we want to do is verify that this reaction is not zero order, not first order. So what I'm going to do is I'm going to go up to my stat plot, second, y equals, and it's still on L1 versus L3 from the last one. So what I'm going to do is I'm going to go into this one and I'm going to make sure that this one is off. And I'm going to go to plot 1 and make sure that that one is on. Whoops. So let's turn plot 1 on. Okay? Now what I'm going to do is I'm going to graph these data, and I've got plot 1 on. It's L1 versus L2. Let's make sure that plot 2 is off, which it is. So plot 1 is on. We're going to graph it, and we're going to zoom to the data. We're going to hit zoom, and we're going to go down to 9, or just hit the 9 button. Ah, you see that weird looking thing right there? Some of my data is weird. I want to verify what is weird, because it should not look like that. Let's go to edit. Aha! That's the weird guy. Let's go here and re-enter. It should be 4400, not 400. Aha! See, it's going to check this stuff. Even the pros make mistakes. I think everything else is cool. Ah! See this one? Should be 241, and it says 0.0041, so 0.00241. Hey, I just did that so you guys could see what it looks like. All right, let's try this again. We're going to go to our stat plot. It shouldn't have changed. It should still be on. Good. Graph, and that looks much better. But it is not a zero order reaction, because that is not a straight line. Okay, it's going to go pretty quickly now. So let's go back to our calculator. We go to our stat plot, and what we want to do is verify that it is or is not a first order reaction. And if it were, it would be a straight line when we graph time versus natural log. So notice how when I highlight L3, notice how the calculator is saying L3 equals what? Well, we want the calculator to take the natural log of everything that's in L2. Remember that L2 is our concentration. So we want the calculator in L3 to take the natural log of everything that's in L2. See that? I just highlighted second, and L2 is the shift function of the 2 button. Boom. This has now taken the natural log of everything that's in L2, and what we're going to do is we're going to graph this. So let's turn plot 1 off, and we'll turn plot 2 on, which you can still see is set up so that L1 is on the x-axis, L3 is on the y. Let's graph it, and we're going to zoom 9. Also, not a straight line. So that leaves us with one final option. And what we're going to do is we're going to tell our calculator to take our data, and we're going to edit it. We know it's not a zero order reaction because it wasn't a straight line when we graphed straight concentration. We know it wasn't first order because it wasn't a straight line when we graphed natural log of concentration. So what we're going to do, the calculator, we've highlighted the top of L4. The calculator is asking us, what do you want L4 to equal? We want it to be the inverse of concentration, the inverse of L2. So I'm going to tell the calculator to take L2 and invert it. When I do that, okay, now just to verify, check it out. This is L1.01, okay, 1 over 100. That's what it looks like when we invert it. Let's go to our graph. We are going to turn off plot 2, and we're going to turn plot 3 on. We're going to instruct it to graph the time on the x-axis, and on the y-axis we want it to be L4. So I'm going to highlight L4, and we're on. Let's graph it. Zoom to the data. Zoom 9. That is a straight line. It is clearly a second order reaction, and that means that the integrated rate law looks like this. 1 over the concentration of C4H6 is equal to KT plus the inverse of the initial concentration of C4H6, which of course is 0.01 right here. And it follows that it has a half-life is 1 over the rate constant K, which we don't quite know yet, times the initial concentration, which we could simply say C4H6O, which means at time 0, or we could write it like this. Okay, but we don't know K yet. So what we're going to do is we're going to solve for K. Now, I already showed you how to solve for K using this rate law, and we're going to do it that way, and then we'll do it by doing what's called a linear regression. So we're simply going to pick a time. So we're going to say K. How are we going to find K, the value in units of the rate constant? So let's pick time, 1,000 seconds, and the concentration is 0.00625. So 0.00625 is equal to K, which we don't know. We picked 1,000 seconds, plus the inverse of the concentration at time 0, which is 0.01. Okay, so to get K, we're going to subtract this from both sides and divide by 1,000 seconds. And let's keep the units in here so we can see what happens to the value of the rate constant K. So K is going to be equal to 1 over 0.00625 moles per liter minus 1 over 0.01 moles per liter. And all of this is divided by 1,000 seconds. When you invert moles per liter, you get liters over moles, and nothing cancels seconds, so our units are going to be liters over moles times seconds. Let's turn our calculator back into a calculator, and we'll say, now watch this, we're going to say that, we'll say 0.00625 inverted minus the inverse of 0.01, and all of this divided by 1,000 seconds. That is our rate constant K, otherwise known as 0.06 liters over moles second. And if you didn't want to do it that way, you could simply linear regress, because this formula is still the formula of a straight line. So all we have to do is go to our calculator. We know this is our straight line, so let's go to our data and let's tell our calculator to run a linear regression on L1 versus L4, and this is going to tell us the slope of our line, which should be K, should be a positive number, and we'll say calculate. Ladies and gentlemen, 0.06. So you verified that K is 0.06 liters over moles seconds. And if you wanted to find the half-life, T1/2 is equal to 1 over K times the initial concentration, 0.01 moles per liter. Now watch what happens when we do this with the units. K is 0.06 liters over moles seconds, and the initial concentration is 0.01 moles over liters. Moles cancels, liters cancels, and all we need to do is we're going to take our calculator and we're going to put 0.06 times 0.01, and we'll take that answer and invert it, and that is our half-life. 1,600. Oh, that's kind of an even number. 1,667 seconds. Does the data support this? If this is 1,000, it would be a half around 0.05, which would be right there in the middle. So yes, the data supports this answer, and that is a second order reaction.